So far we have discussed the properties of set, of different operations on set, that is the set algebra. We define different types of sets. Now, once we have an idea about set, we want to extend it to a sequence of sets. What do you mean by a sequence? In this lecture, I will try to cover these topics, that is sequence of sets. Once you have a sequence, then whether the limit of that sequence of sets exists or not, what are the conditions. In this regard, I will be describing limit superior or lim sup and limit inferior or lim inf of a sequence of sets. Once we have this lim sup and lim inf with our hand, we will try to using this definition, we will try to do some work to find the limits of some sequences, and we will try to find these limits using some examples. Once we have this lim sup and lim inf, then we will try to focus on another important aspect is called indicator set functions. These indicator set functions, they have a very important role to play in subsequent lectures. So, we will be putting some emphasis on this indicator set functions. So, we will start this discussion with the definition of sequence and subsequence. So, what is the definition of a sequence? Mathematically speaking, suppose the script n is the set of 1, 2, 3 and so on, and a sequence is a function f which maps n to r. Script r is the real line, and it is represented by x n is function of n, where n belongs to script n. A sequence can be given into different ways. We can express a sequence in different ways. The first way is obviously by listing the elements. So, I can have a sequence something like that: 1 by 2, 2 by 3, 3 by 4, 4 by 5 and so on. We can give a formula to generate the terms. For example, x n equals to minus 1 to the power n, 2 to the power n over n factorial. So, if you put n equals to 1, it will be minus 2. If we put n equals to 2, it will be plus 2 square over 2 factorial and so on. Sometimes a sequence can be given recursively too. So, first giving the initial, that is x 1 is 2, then the recursive relation between n plus 1th term and nth term can be given in this way: x n plus 1 is half of x n plus 6. So, if I put n equals to 1, then x 2 will be half of x 1 plus 6. So, this is a sequence. So, whenever you have a sequence, from that sequence we can construct subsequence. How? Well, suppose I have a mapping from n to r denoted by f, then I have another mapping G which maps n to n such that Gk is Nk, where we have a restriction that n1 is less than equals to n2 is less than equals to n3 and so on. So, this is called a subsequence. It is composite mapping. So, from the collection xn, this is my sequence, we can get a subs collection xnk with n1 less than n2 less than n3, and this sub collection xnk is called the subsequence. Now, consider a few examples. Suppose I define nn is the first n natural numbers 1, 2, 3 up to n. Then this nn is a sequence of subsets of n. Script n is the set we defined earlier. For each n, we can define an interval in, where we say that it is a set of all x belongs to the real line such that x lies between 0 and 1 by n. So, this is nothing but an interval, open interval 0 and 1 by n. This is a sequence of subsets of R. This is the real line. Now, what are the operations, what are the algebraic operations that can be done on this sequence of subsets? So, what will be the unions, what will be the intersections? Results about finite intersection and union of sets remain true in these settings. So, whatever we obtained in case of set theory, those results will remain valid. Suppose A n is a sequence of sets. We say that A n is monotonically increasing with n. That means, if n increases, A n will also get increased. If we have A n strictly or proper subset of A n plus 1 for every n in the domain of the sequence. Let us take one example. Suppose A n is an interval 0 n. So, if I increase n, each time this interval will get bigger and bigger. So, if I take a sequence of these intervals A n, they will be monotonically increasing. Similarly, we can have monotonically decreasing sequences too. So, if we have A n is a proper superset of A n plus 1, that means as n increases, if the set is getting decreased, we say that sequence is monotonically decreasing. Take this example of an interval 0 1 over n, 0 closed 1 over n open. So, if I increase n, every time it will get reduced. So, this is an example of monotonically decreasing sequence. Once we have the concept of monotonically increasing or monotonically decreasing sequence, now we will define limit superior or limit inferior of a sequence of sets A n. So, we define lim sup A n as intersection n from 1 to infinity, union k from n to infinity a k, and in case of lim inf, it is just the opposite, interchanging the union and intersection. So, I will be describing the definitions in more lucid way. So, we define B n as union over k from n to infinity a k. This is the part you will find in the definition of lim sup of A n. Now, B n is a monotone sequence. Now, whether it is increasing or decreasing, let us see. If I increase n, what will happen? K runs from n to infinity. So, if n increases, I am taking lesser number of unions. That means, I am reducing the B n. So, B n is decreasing in n. Whereas, if I define C n as the intersection part that is found in the limit definition, then it can be seen that if I increase n, that means I am taking lesser number of intersection. Once I am taking lesser number of intersection, I am getting bigger sets. That means C n is increasing. So, whenever you are talking about the limit of an increasing sequence, then it must be going to its union. Whereas, whenever we are talking about the limit of a decreasing sequence, then its limit must be going to in its intersection. So, using this notion, we can define B as the limit of B n is intersection n from 1 to infinity B n, because B n is decreasing. So, its limit will be its intersection. So, this is nothing but lim sup of A n, and C is limit C n, and we can see that C n is increasing, monotonically increasing. So, its limit will lie into its union, and this is nothing but lim inf of A n. So, thus we have defined lim superior of a sequence of event A n, I should say sets, and then we will have lim inf of a sequence of sets A n. So, we call lim sup and lim inf. Now, we will try to find lim sup and lim inf for a number of cases. Take the first example. Suppose A n is defined as 0 1 or 1 2 according to n is even or odd. So, that means if n is 1, that is odd number, then it is 0 1. If n is 2, that is even number, then it is 1 2. Now, going back to the definition of limb soup, the first thing you have to take is the union k from n to infinity a k. So, if you take the union of the sets 0 1 and 1 2, you will get a set 0 2. But if you take the intersection of these two sets, you will be getting phi. So, after doing some algebra, it can be shown that the limb soup is 0 2, whereas limb inf is phi. These two are not equal. Now, we focus on the second example. This is a set of n is defined as collection of x and y such that x lies between 0 and n and y lies between 0 and 1 over n. Now, we have to find limb soup as well as limb inf. If we compute the limb soup, it will be something like that: n from 1 to infinity, k from n to infinity, x y, x lies between 0 and k, and y lies between 0 and 1 over k. So, whenever we are taking union, first union, that means we have to take the larger sets or the largest sets possible. So, in this case, k will be going to infinity, and for y, the largest interval that I can have is achieved when k is equals to n. So, it will be 0 to 1 over n. Now, we have to take the intersection. So, that means now we will have to consider the smallest set, because we are taking the intersection. For x, it is independent of n, so nothing will happen to the limit of x. But if you see, in case of y, the intersection will reduce the case to be y equals to 0. So, limb soup of a n is collection of x y such that x lies between 0 to infinity and y is equals to 0. Now, we consider the limb inf. Proceeding in the same way, we just define, we put the definition here, and first we have to take the intersection. That means we have to take the smallest or smallest sets. Then, in case of x, the smallest can be achieved when x is equals to n. That is why x lies between 0 to n, and for y, y is equals to 0, because we have to take the smallest set. And now, we are to take the union over n from 1 to infinity. In case of y, it is independent of n, so it will remain all the same, but in case of x, it will be 0 to infinity. So, the limb inf is collection of x y such that x lies between 0 to infinity and y is equals to 0. Here, we found that limb soup is equals to limb inf. So, whenever we have limb soup equals to limb inf, we say limit exists. Now, we will take a few more examples. Consider the interval a n defined as 0, 1 minus 1 over n. Now, if we start with the limb inf, by definition, it will be n from 1 to infinity, k from n to infinity, 0, 1 minus 1 over k. Now, the first case you have to take the smallest of these intervals, and then you have to take the union over n from 1 to infinity. After a closed loop, it can be seen that this limit is 0 to 1, this interval, which is same as limb soup a n. So, here also the limb soup and limb inf coincides, and we say limit exists. In general, limb inf is a subset of limb soup. The proof is not very hard to understand. Now, we know that k from n to infinity a k, if I take intersection of so many sets, will be a subset of k from n plus j to infinity a k. This is because in the second set, we are taking less number of intersection. Whenever we are taking less number of intersection, that means the set is getting bigger. Now, we know that intersection is a subset of union. So, if I interchange the sign, then intersection replaced by union, so it will be again a proper subset, and this is k from n plus j to infinity union over a k. If we start from, instead of n plus j, if we start from k k equals to j, that means we are taking more unions, that means we are getting bigger sets. So, it is again a superset of the previous set. So, after doing this calculation for any n and j, we get this, that k from n to infinity intersection of a k is a subset of union over k equals to j to infinity a k. Now, the left set is independent of j and the right set is independent of n. So, if you take the union over n from 1 to infinity to both the sides, the right side will not be altered, or if you take the intersection over n from 1 to infinity, the left side will not be altered. So, keeping this thing into mind, we can easily get that lim-inf is a subset of lim-sup. Once we have this lim-sup and lim-inf, now we have a very important theorem. It says a monotonic increasing sequence or decreasing sequence a n is convergent, and limit of this convergent sequence will be its union or intersection. If it is increasing, it will go to its union. If it is decreasing, it will be going to its intersection. Well, the proof is something like that. Suppose that a n is monotonically increasing in n, then lim-sup of a n by definition, this is the limit, this is the definition that we have, k from n to infinity a k, and we have the intersection outside. Now, this k from 1 to infinity a k is same as a n is increasing. So, whether I am taking the union from the n to infinity or 1 to infinity, they remains the same. So, this term k from 1 to infinity a k union over a k does not depend on n. So, if I take the intersection, it will not hamper. So, the lim-sup will be just its union. Similarly, if we have lim-inf of a n, by definition lim-inf is union and intersection k from n to infinity a k. Now, this is increasing sequence. So, this intersection of k from n to infinity will result in a single set a n. Then lim n infinity or lim inferior a n is just its union n from 1 to infinity a n, we call lim-sup of a n. So, this theorem, this result we have proved for increasing monotone increasing sequence. It can be seen for the decreasing sequence also, the proof will remain almost the same. This is the last topic that we will be discussing here, is the indicator function of sets. We define IAW is 1 or 0. It takes two values, 1 or 0, whether depending on the belongingness of W to A. So, if W belongs to A, we say it is 1, and if it does not belong to A, we say it is 0, that is W belongs to A complement. Once we define this indicator function, these are the few results that immediately follow, that I A complement W will be 1 minus I A W, I of A intersection B W will be I A W into I B W, and I of A union B will be less than equals to I A W plus I B W. These are the three important results that immediately follow. To prove or to describe two more results, we define partial sums as S1 is the sum of j from 1 to n I A j W. S2 is the sum of j1 and j2 and j1 less than j2, both ranges from 1 to n I A j1 A j2. So, this A j1 A j2 I A j1 A j2 will contribute if and only if W belongs to both of these two sets. Similarly, Sm is defined as I A j1 I A j2 I A jm. So, I am considering m sets A j1 A j2 A jm. If W belongs to all these m sets, this will contribute, and the sum is over j1 j2 jm, all ranges from 1 to n, with the restriction that j1 is less than j2 is less than j3 and so on. And Sn is the set which consists of all n sets I A j1 A j2 A jn. So, if omega belongs to all of these n sets, it will contribute. Under this setup, we have a result that W belongs to at least one of these AIs, at least one of these sets can be expressed as S1 minus S2 plus S3 minus S4 so on plus minus 1 to the power n minus 1 Sn. The proof is however a bit simple, I should say. So, to prove this, we will take the contribution of an omega to the left hand side as well as to the right hand side. Now, if omega does not belongs to any of these AIs, then the contribution to the left hand side will be 0. So, omega does not belongs to I from 1 to n AI means omega belongs to I complement for all I. That means contribution to the S1, S2, S3 all will be 0. If omega belongs to at least one of this, so that means I from 1 to n AI, then left hand side will be 1, and for the right hand side to find the contribution we will say that, well, let us assume that omega belongs to exactly m of the sets A1, A2, Am. Then in case S1 the contribution will be any m sets, any 1 sets out of these m sets, it is m choose 1. For S2 the contribution will be, it will belong to 2 sets out of any m to m sets, so m choose 2. So, it will be m choose 1 minus m choose 2 plus minus 1 to the power n, m choose m. So, after applying the binomial theorem, it can be shown that its the sum is 1. So, right hand side is exactly equals to left hand side. Similarly, if we have a set Bm is a set of points belonging to exactly m sets, we can show that IBM is Sm minus m plus 1 choose m, Sm plus 1 plus m plus 2 choose m, Sm plus 2 and so on. Well, the proof is a bit tedious compared to the first one. So, we will assume that I will give a sketch. We assume that W belongs to exactly k sets. When k is less than m, the contribution to the left hand side as well as to the right hand side is equals to 0. If k is equals to m, the contribution to the left hand side is 1 and contribution to the right hand side will be 1. The contribution will come only from the Sm, and if k is greater than m, the contribution to the left hand side will be 0, and after doing much computation it can be shown that the contribution to the right hand side is also 0. So far we have discussed sequence, subsequence of sets. Then we also have discussed limit superior or lim sup or limit inferior or lim inf of these sequences of sets. We try to find these limits using some examples too. Then we define the indicator functions, which are very important when we will be dealing with probability measure. So, once we have gone through all these concepts, now we will try to shift our concentration to field and sigma field and a special type of sigma field called Borel sigma field or Borel field in subsequent lectures.